so let's do. Today we're still looking at 2.4, so that homework will be due tonight. We're finishing up chain rule and implicit. We'll do a couple more examples in class and we'll get some homework problems if you want. Tomorrow we start 3.5, which, if you want to flash forward, problem number 86. Is that one? Nope, we skipped that one. Problem number 87, one-year homework problem. Very similar to what we're going to do in class tomorrow. So, basically, tomorrow's section is a whole application of implicit. Right, and then again, chapter 3 is mostly application, so we kind of sprinkled them in a little bit in chapter 2 to spread it out. All right, so we have that on Wednesday, and then the quiz is on Friday this week. Okay. So let's make sure we're on top of when everything's due. All right. So I wanted to do maybe a warm-up problem. Let's say we have f of x is x cubed times x squared plus 1 divided by 3x minus 1. Actually, just make it look worse. Raise that to the fourth power. And pretty much our goal is always, can we find the derivative? So I want to find the derivative of all of this. What rule do I use first? Yeah.
Okay. Wouldn't you need the quotient rule?
At some point, I definitely need a quotient rule. Is that the one I want to do first? What rules am I going to need in this problem?
And product.
Quotient rule, chain rule, there's a product in the top. That's the one that is easy to miss. People usually get the quotient rule right and forget that there's a product rule. So I definitely need a product rule, quotient rule, and the chain rule because of this fourth. Or I'd have to multiply all that out, which I don't want to do any of that. In theory, I could expand all of this, multiply through by x cubed, and avoid two of the rules. But that wouldn't necessarily make my life any easier. I'm going to make this look a little bit worse. For some reason, we see things like this on the final sometimes. Now, what would be your first step?
I mean, the derivative of
The two problems? All right, that one, it's a little easier to see what should be my first step, just breaking the two problems. And then what would it be over here? I could say plus the derivative of 17x. What's the derivative of 17x? 17. You've done enough practice where you can kind of fill in the blank sometimes. All right. So I'm back to, I want to take this derivative. I think I remember quotient rule first. Let's do that. So, because I have a quotient, I use the quotient rule. What's the quotient rule say?
Derivative of the top multiplied by the bottom minus the top times the derivative of the bottom divided by the bottom squared. I think.
Put a confidence there at the end. And then I have to write plus 17 because I made the problem awful where I have to write plus 17 every single time. And this is part of this lesson is don't forget to write plus 17 every single time. If you just write it at the end, now you change the problem twice. You can always keep writing plus 17, it's not going to work. Same way, people like to do the quotient rule and not write the divided by the bottom square. And then it's 50-50 if they ever go back and divide. Just write everything. Alright, so quotient rule said bottom function times the derivative of the top function. Did I take this derivative? I just said I need this derivative, right? Just put in the placeholders. Minus the top function times the bottom, all the bottom square. This one, what's the derivative of 3x minus 1?
3.
3. Had you just written a 3 here and not written all of this, that is perfectly fine. That is one that you could probably look at, say the derivative is 3. I don't need the ddx symbol anymore because I already found the derivative. The problem is if you do that, make sure you don't write ddx. Like, pick one. You can either take the derivative and write it in line. I would still put it in parentheses so I know where it came from. Like, I wouldn't immediately go move it to the front of the problem because why is there a random 3 here? So I'd leave it in place just so you know where it came from. That way if you're going back, you know where things showed up. So you can do that part either way. The other one, the derivative of x cubed times f, I would definitely not do that in line. I would wait for the next step. That one has a lot of effort involved. So you don't want to, anything that has a lot of effort, just leave it for later. Right? Simplify as you go, or do the next right step or the next step, but don't do so much at once that you don't know what happened or you lose things. So then, what would I do next? How many more derivatives do I need to take? I only got one ddx symbol, right? So, yeah, that one looks involved, but if I want to finish, all I have to do is clear out this ddx. Okay, so I get equal to 3x minus 1. Put a big curly brace here. What do I need to take the derivative of this? Somebody, I mean, we've mentioned we need a product and a chain rule. Which one comes first?
Product.
I have, so people are saying chain because this is to the 4th power, but it's only this part to the 4th power, not this part. So really, before doing a chain rule and dealing with this 4 power, I have to take into account I'm multiplying 2 things. Because I have this times this, the first thing I need to do is the product rule because this 4 doesn't apply to this term. Alright. So what would the product rule say? Take the first function, multiply by the derivative of the other function. Then add the derivative of the first function times the second function. And that's it, right? This ddx symbol, I need to take the derivative of this. This requires the product rule. So everything here this whole piece becomes everything I just wrote in a curly brace. Which looking at now looks terrible, but what I do is product rule, right? If I look at that piece and the one that came before it, it makes sense where it came from. Hopefully. Doesn't matter that it's that long. Does that really hurt us in any way? I think the best decision I ever made in math was I started using inline paper and just killing more trees and doing like one problem per page and just showing more work. Instead of trying to cram it all on the front side of one page with college rule, where you could write like a fraction in that much space, spread it out, show more work, suddenly you stop making as many mistakes. Alright, so this piece becomes that whole piece there. Then what about the rest of it? Yeah, just copy everything else that you see. None of these have ddx symbols anymore. Assuming I already, otherwise I'd maybe do this one on the next step too. But assuming this has no more ddx's because I already found this 3, I just copy everything. And for the rest of the problem, all I'm going to do is copy that. So this is going to be minus x cubed times x squared plus 1 the fourth power times 3, all divided by the bottom squared. Do I ever multiply out the bottom squared? That's like completely backwards, right? Don't mess with it, don't expand it out. We're not asking you to like multiply everything out every single time. That's really just a waste of time. We're just trying to see, can you find the derivative? Okay? There's no reason to multiply all of this out. And then I have my plus 17 hanging out. Is that line equal to the 1/4? You're going to check, what do you do? Make sure I just copied everything and then the purple part changed? And then what I do in the purple part, only the product rule? So I make sure I did the product rule correctly, had the two terms, put a plus sign, looks good. Alright, so what's the last thing I need? Yeah, deal with all of this. So what would this, x cubed times this derivative, what is this derivative? I have something to the fourth power, or a bunch of things to the fourth. So I need a chain rule. Finally using the chain rule. We could see we needed it, but we're only now using it. So chain rule says, bring down the 4, subtract 1. So I basically do a power rule. But then, because of this term, I need to multiply by the derivative of the inside. What is the derivative of x squared plus 1? 2x. If you want, you could write d dx of x squared plus 1 to remind yourself where this came from. Or really, when I see this, I know this must be the derivative of this, if I'm always consistent. So again, show the number of steps you need. You can put the d dx there and find it on the next step. That is fine. There's always some students worried about what am I allowed to not show, so I'm trying to show a little bit less. You can do things in line. We're not saying you can't, but we also don't want you to make mistakes. So that's where it's a little bit, as you practice, you'll get more comfortable with what do you need to show every time, what could you maybe do on the fly. But there's a balance there for everybody. Is that the derivative of this? Let's look backwards. Is this the derivative of this? Am I done with it?
Wait.
What's that?
Yeah, all I have to do is find the derivative of this. Derivative of this, do the chain, or power rule with the chain rule to get the 2x. And that's the whole derivative, right? So now what? Move on to the next term. I found the derivative of this, it became this. So now I just keep going through here. What else was next? I need the derivative of x cubed. What is that? X squared. And then this one was still hanging out. Minus x cubed times all of this. And I'm just rewriting everything else we have. Am I done?
That's your derivative.
Are there any more DDX symbols? I applied basically one rule at a time. Got to this answer, or got to this part with all the equal signs. There's no more DDX symbols. That means I have found the derivative. Anything I do from here on out, I'm not taking derivatives. I can just simplify this to make it maybe look a little nicer. So we would say that's just doing algebra afterwards. You can clean it up if you want. You also don't need to. If you go to the back of the book, they typically have it looking like that. I will not count off if you leave a problem like that where you found the derivative. I will not count off if you simplify and get a nicer answer. I will take off 1 point if you simplify and do something wrong during that simplification. And then sadly in chapter 3, you will have to simplify every time. But that's actually a little misleading. In chapter 3, you'll need to find when is the top equal to 0, when is the bottom equal to 0. So, because we know when's the bottom equal to 0, definitely don't expand this, right? It's already factored, I could solve that more easily. The top, I could do a lot of factoring and rewrite, and I would have to do that in chapter 3. But in chapter 3, we also typically don't give you this problem. So then it doesn't matter as much. Like this would be on the upper end of how hard it would be to simplify, and typically it doesn't actually show up in chapter 3, this pattern. Right. Chapter 2 is more, do you understand the derivative rules, and those could be complicated problems to get to an answer. In chapter 3, we're doing more with it, so we can't give you the worst derivative ever because we didn't want you to do something else. Right. So that's another reason we kind of don't have the big emphasis now on simplifying. These would be harder to simplify than what you actually need to do in practice. Any questions on that one? That's worse than any of the homework, except for that one problem we started a couple days ago. Yeah. I finished it today with a student. So it has been finished by one person, maybe more. All right. So, I mean, that includes every derivative rule we've covered up until now, basically. The other part of this section is implicit. That I want to look at. This person has better handwriting than I do. I know that's what you're all thinking. 1, oh man, more math, but then 2, that is much better handwriting. Hey, those come up in here too. We'll just leave those. All right. So the other one we'll look at is implicit. I wanted to do, last time we talked about why we need implicit. Now we want to actually do another example. Okay. So yesterday was kind of why we have implicit, where it shows up, what we need to be able to do. Here we want to do one that looks way worse. So which one is in the homework? So I'll do that one.
Is 57 an implicit problem? I mean, because I got no idea how to cover that.
Are we?
D over dr RS squared.
Okay. Yeah, we do 57. Technically, no, but it's worth looking at.
Okay.
And then we'll do implicit, because it builds some ideas. So 57 was more, do you understand this Leibniz notation? So I want to find the derivative of r times s squared. And before it says r is the independent variable, s depends on r. So my independent variable is r, and s depends on r. So think of it as s of r. We're just not writing the r in there. So if we want to find this, what it's really saying is find the derivative of the expression r times s of r squared. Instead of writing f of x, it's s of r. And it's saying the variable that we care about, the independent variable, is r. So this is a function of r. This is also a function of r. Does that make sense? It's kind of like if this was x times y of x or f of x. It all depends on, we're thinking of x as the variable, now we're thinking r as the variable. So this tells you the variable that we care about. If I do a power rule, I need r to a power to use the power rule. So what derivative rule do I need first? Yeah, I have something here, r, and then this, which is another function of r. So I have two things that depend on r that are multiplied. So I have to use a product rule first. So it's r times the derivative of s squared plus the derivative of r times s squared. Now, we usually don't write of r because the notation becomes awful. In theory, we should. So let's switch to this one first. What is the derivative of r with respect to r?
Huh?
So notationally, I do d dx of mx plus b. What's the derivative?
Would be m, so would that be an identity function and make it equal to 1?
Yeah. So this is a line with respect to x, right? When I write just r here, this is a line with respect to r with leading coefficient 1. So slope is equal to 1. So plus 1 times s squared. What about this one?
R times 2s times some derivative of,
So this is some function of r squared. So I have something on the inside all squared. So when I take the derivative, I have to bring the 2 down. And then I have this all to the first power. And now I use the fact s depends on r. So I need the derivative of s. So if I want to simplify this just a little bit, it's 2 times r times s times the derivative of s with respect to r plus s squared. Do I know what s is? I just said s depends on r. I never told you how. All right. Another way you might write this is s prime of r. The derivative of s with respect to r. So if you write the prime symbol, it's saying the derivative with respect to the independent variable. The independent variable is r. Usually I don't write primes when I'm mixing up letters. Because then what does the prime represent? So now, I mean, the beauty here is we know the answer for any function s. What if s was a constant function? If it's a constant function, does it depend on r? Technically, no. So the derivative here would be 0, and this would just disappear. What if it's a linear function? I can find this derivative and then use that. So like for any function s, I can do this. If s doesn't depend on r, that just means it's constant value. But then that's okay, because anywhere I have dsdr, this is constant value, I would get a 0. So it works. It's a generalization. It works in general. It doesn't matter how s depends on r, this formula holds. If s just happens to not depend on r, that means it's constant value, so all these derivatives would be 0. Kind of like if you write, what is the derivative of 3z plus 1? If z is a variable, or if z doesn't depend on x, I'd get 0, right? Because it never depends on x. If z does depend on x, I'd get 3 dz dx plus 0. What if I don't know? Then this is the one that says if z depends on if this variable z depends on variable x, I need to calculate this. If I happen to know z doesn't depend on x, this is 0, so nothing changes. So it's kind of like the general one. If this letter depends on this letter, I need to be able to compute this at some point. But the formula holds in general. If it happens to not depend on it, I just get a 0 from it somewhere. But until I tell you what z is, you don't know, right? What if I did plus x here? Or x squared. What's the derivative of x squared with respect to x? That's power rule, right? So I just put in the 2x. So like, I can do derivative rules when the variables line up. What about when they don't line up? Then I just put a placeholder in and say, this derivative, now if you tell me what a z is or how it depends on x, I can fill in the blank here. Otherwise, just leave it as a symbol.
So that right there, under the final equal sign, that's the form that the answer would have to take?
Yeah, this one?
Yeah.
Yeah, that'd be the easiest. Unless you know more about s, which we're not given in this problem, that's the best you can do. But it accounts for everything. It accounts for if s depends on the variable r, it also accounts for if s doesn't really depend on the variable r. Because all that's built into what this means. This means the derivative with respect to r.
What about number 87?
Hmm?
What about number 87?
I want to do another implicit one first before I do another problem. Good try. What number was that?
87.
57?
87.
87. I think maybe do 87. I was looking for a related rates problem. That's as good as any. See how much time we got. Alright, so I want to look at number. Which one do y'all want to do in the block 69 to 80? That is not number 71. Because I assigned number 71. Anybody have one that looks particularly awful they want to do? That'd require a template. Alright, 74 looks gross. That's a great reason to pick it. I thought that was before. 74. We have the implicit equation x squared y minus y squared x is equal to x squared plus 3. Now I want to find dy dx. Anybody have any clue what that looks like?
Don't we need the product rule twice?
Yes. Stop. Let's see what this looks like. Alright, so y'all said this is gross. Let's see if you're right. Yeah, that one's fun. That is that function or that graph. That is, I'll go with gross. That is definitely not a function. All the x, y values that satisfy that equal signs are either on this piece, or that piece. I would definitely not guess that. That's the nice thing. I have no idea what these graphs look like. You don't have to actually use these methods. But what's the goal of the problem? The goal is, can I find tangent line, or the slope of the tangent line? If I give you this point, can I find a formula that tells me this slope? If I give you this point, can I find a formula for this slope? So when we do this, we'll end up getting a formula in terms of x and y that if you give me the xy coordinate pairs, I can plug it in and it would tell me the slope of the tangent line. And then if you give me an xy coordinate pair here, it'll still give me a value, and it's wrong because it doesn't apply. So that's always the dangerous part about these. I can plug in any xy values. The only ones that would be relevant for this problem are the ones based on these red curves. Anything else, if I think this xy coordinate pair, the formula will give me a number, and that number has no meaning. Alright, so that's always the weird thing implicit. Hey, we told you vertical line test. How many times now? We're finally not doing the vertical line test. We failed that horribly. Like we told you early on, don't divide by 0, and then we spent, what, 3 weeks doing 0 over 0? And then we said, make sure you pass the vertical line test. Now we're failing the vertical line test. So the idea is, my y coordinate depends on my x coordinate. Right? But I don't really, they depend on each other, that I must solve this equal sign. I still don't really know what those are, but they do depend on each other. So the idea is, just work directly with what we're given. If these two things on the left and right are the same, that means I should be able to take the derivative on the left, the derivative on the right, and they still be the same thing. Equal means these are the same no matter what. So then they must have the same derivatives. So I need, on the left, the derivative of x squared times y, and then subtract the derivative of y squared times x. And what is the derivative of x squared plus 3? Just 2x. That one we know, right? My variable is x. I don't have any y's floating around here. If I want to take the derivative with respect to x, I have x squared, do a power rule, I have 3, that's constant. This derivative would just be 2x. As long as the variables match up, this is what we know how to do. That is like when you say f of x, find that prime of x. It's when the variables don't match up, when I get these combinations, that I have to be more careful. So how do you find the derivative of x squared times y? Again, I don't know what y is, but y is some function, I shouldn't say function, but y depends on x, right? So treat it like it's its own thing. So when I see this, I think of it as I have the function x squared times some relationship y. Y depends on x. Now if I'm multiplying, that means I need a product rule, right? So if I have two things, I do the product rule. Is that believable for the product rule? And then what about this one? I would get minus, and then what do I need here? Y squared times x, right? So I have something times something else, y squared times x. I still need the product rule. Right. So product rule says y squared times derivative of x plus derivative of y squared times x. And why did I put a big curly brace around it? Yeah, I don't want to lose this negative sign sitting here. So now when I do the negative sign, it's everything that's inside here. And all this is equal to 2x. That right hand side was a lot better. Alright, so what is the derivative of y with respect to x? This is where we just play with notation. Yeah, I just write dy over dx. Somebody always does this. Some students really like prime, so they put y prime. Why am I not putting y prime everywhere? It is easy to misread y prime as y squared or something else. That prime doesn't really look like anything sometimes. If you write dy dx, you know that is a thing. Right? It's a big symbol that you can then work with. The other one gets lost in notation sometimes. So rarely do, in an implicit, I basically never use prime notation. It's It's not wrong, but it's easier to make mistakes sometimes. What about this one?
2x.
Greater than x squared is 2x. And then I just had a y here. Minus y squared, what's the derivative of x with respect to x? 1. Plus, now the hard one, what's the derivative of y squared?
2y.
I think of y as depending on x, so I treat that as an inside function that is all squared. So I have something inside a square. So I want to do a power rule, so I bring the 2 down. So I get 2y to the 2 minus 1 power. But then my inside part was y, so I have to multiply by dy dx, the derivative of y with respect to x. So I'm just treating y like an inside function every time I do anything. And then what's left over? Times x. So if I distribute this, minus y squared minus 2 times y. I'm going to put the x in front. dy dx, all equal to 2x. At this point, I am 95% done. Maybe not 95. 88 done. What's left? My goal is to find dy dx.
Subtract all the terms from the left side that don't have dy dx.
Where is dy dx? It's here and here only, right? If I want to find it, that just means I need to get it by itself. Solve for it. So now I'm going to solve for dy dx. So on the left side, I get x squared times dy dx minus 2y times x times dy dx. And I put everything else to the right hand side is equal to negative 2xy. So I subtracted this term over. This one doesn't have a dy dx in it, right? So I added over. So plus y squared. And then I still had a 2x sitting over there. So I got the purple ones. Anything that had a dy dx, I left on the left. Anything without it, I moved to the right. Ends up, you can always do this. It'll always work out where you can factor it out this way. So then what's the next line? Had there been a y over here, I'd have a dy dx over here on the right. What would I do there? Anything with a dy dx on the right, move to the left. My goal is to get dy dx by itself, so I put them all on one side. And now what can I do? Yeah. It's always, it'll never be like dy dx squared, or dy dx cubed, or cosine of dy dx. Nothing bad is going to happen there. I can always factor it out. That always happens when you do this. So I have a dy dx, I have a dy dx, that means I can always write it on the right hand side. And then just write what are the coefficients. I have an x squared, and I have a 2 minus yx. Or minus 2yx. Equal to all this. So then what's the last thing? I want to get dy dx by itself. I have a bunch of stuff times dy dx is equal to something else. Divide everything by this parenthesis. If I want to get dy dx by itself, I have all of this times dy dx, so I divide everything else over. And I get to this one. Which is a somewhat amazing formula. We showed the graph. That was an awful looking graph, right? Well, not awful looking, but definitely not a trivial graph. There's a lot going on there. And this says, give me any XY coordinate pair on that graph. This is the slope guaranteed. Did we do any really hard rules when we were doing this? I mean, it looks involved, but did we do any really hard derivatives beyond what we did doing? No. The new thing is just remembering how to do the chain rule part so that we get to dy dx as a shown for. And then the last step is get it by itself. They always kind of play out that same way. And it looks in some ways much worse than it is, hopefully. All right. Any questions on that one? So I'll set up a word problem for you. All right, so that's about 87. Now I'm talking about area of a circle. So area of a circle is pi r squared. And the idea is the area depends on time, and the radius depends on time. So usually the way these show up is, think about if you drop a rock into a pond, what happens? It splashes and you get this circle that keeps growing. So you drop your rock into a pond, it splashes, a second later, this is that outside wave kind of moving away from it. Then you wait a little bit longer and it gets bigger. And this keeps, as time progresses, this circle gets bigger and bigger. That's what we're kind of thinking about here. The radius of this circle depends on time. If the radius changes with respect to time, what does that tell you about the area? If I change this value changes, right? So really, if this depends on time, this one does also. Or vice versa. If the area depends on time, the radius must be changing. All right? So part A says find dA dt. All of these are going to be implicit differentiation. So how do we do that? If we have A is pi r squared, this must be the same as this. That means if I take the derivative on the left and the derivative on the right, they must be the same thing, right? What is my underlying variable? Time. It says the radius depends on time. The area depends on time. So my independent variable must be time. When I write ddt, I don't write ddx, I write ddt. It depends on time. All right? This is always your independent variable part down here. So then, what is this? Usually we just write dA dt. There's nothing left there, right? A depends on time. The derivative of A would just be dA dt, or A prime of t, if you wanted to write it that way. Usually we don't. But it's kind of the same idea here. What about on the right? Pi is a constant, but then I have r squared. R is a function of time. So I want to think of this as r squared is r of t all squared. So how do I find that derivative? I have something on the inside squared. I want to take the derivative.
Chain rule.
I need a chain rule. Bring the 2 down. Get r to the first power. And then multiply by the r dt. So like if I took the derivative here, I'd bring the 2 down, RT to the first power times R prime T. We just write that in this notation, bring the 2 down, leave the R to the first power times the RDT. So I end up with the ADT must equal 2 pi R the RDT. So what's takeaway here? If I know how fast the radius is changing, I can measure that, right? You see your radius getting bigger, you could measure it with a stopwatch, I guess, see how fast the radius is increasing or decreasing, see how fast it's changing. If I know how fast the radius is changing, what does that mean for the area? It's changing at the same value times 2 pi r. So whatever this is changing at, this rate, the other one is the same rate times the number. The interesting 2 pi r showed up. Remember, what's the 2 pi r give you? Circumference of the circle. The rate of change of the area is based on the circumference. There's always some relationships like that. So we'll see that a lot more in 3.5. So 3.5 is always setting up word problems where basically you need some equation like this, and then you always take the derivative with respect to time. So we call it a rate, kind of like when you're driving down the road, you measure your velocity, it's based on time. Everything is happening at some rate, it's based on time. It starts here, and it keeps progressing to here. If I want to know the rate of change for the area, all I need is the rate of change for the radius. If I know the rate of change for the area, I can solve for the rate of change of the radius. These two variables are related to each other, therefore their rates are also related. So it's figuring out, I know A is pi r squared, what about the rates? How are they equal to each other? What is this relation? It's really just code for doing implicit. Write a formula, do implicit. Alright, so I'll see you all